In this last video segment, we are taking now these dynamics equations of motion for floating-based systems and turning this into control. So what we can do is we can then use this in order to make a system produce certain tasks at the same time. So for example, this humanoid here is moving this one end effector along a predefined trajectory, another end effector along a predefined trajectory. It's ensuring a contact with the environment, certain interaction forces here, maintains its center of gravity above the contact surface, and it's looking at some direction. So all of that is a description of how the system is moving. We see the same thing here also on the right hand side. So we ensure a certain posture, we are manipulating an object, and we have ground contact constraints. Now what you see here is predominantly motion. So how is the system moving? But as we have seen earlier, we're not only interested in how the system is moving, but also in how it's interacting with the environment. If a robot interacts with its environment at multiple contact points, like here 2 feet and 2 hands, there's a certain number of internal forces that this robot can produce. And these internal forces, they essentially change the way the system interacts with the environment, but it does not change the way how the system moves. And by changing these internal forces, we are changing the joint torque distribution, but again, without changing how the system is moving. In other words, that means we can stand or sit in exactly the same configuration while producing different joint level torques. One produces more, the other one less internal forces. So in other words, I can, for example, optimize for the way I'm interacting with the environment. So for example, producing a certain force at a contact point, or I can optimize for requiring as little torque as possible in the joints to be, for example, efficient. And this is pretty much seen when you, for example, walk on a street which might be icy. If you walk on a street that you know for sure you have high friction coefficients, you will not slip at all, you can move while cranking down the muscle activity as much as possible, so to move as efficient as possible. This ensures then, if you're walking and if this is your foot, your lower limb and your upper limb, if you want to reduce the muscle activity, the ground reaction force typically goes roughly through the base. So you have a pretty high tangential force at that contact point. Now, if you would walk exactly the same way on an icy street, like during winter, you would just slip. So what we are typically doing then is we're trying to align this ground reaction force with the surface normal, that we are not slipping at all. But that of course requires more muscle activity in certain joints, and hence it's harder to execute. That's also what you feel, right? If you walk on an icy field, you need more muscle activity to walk there. And this is what we're going to leverage and show you how you can exploit for controlling such robotic systems. In these two videos are two very extreme examples. So see a human walking through a vertical wall. If I would just look at this kinematically, this is absolutely impossible, right? Because kinematically, it doesn't matter whether this hand is just a micrometer a little more to the left or not, and it's undefined how much force we're producing. But only by looking at the full dynamics, we can then produce here a reaction force between the wall and the hand, which allows us to produce all the tangential force and hence to propel the person here upwards. To achieve this, what we want to do is inverse dynamics control with floating-based systems, so systems as we see in here. And again, like the big difference is these systems are in contact with the environment, so we have to consider also the interaction forces with the environments. As a quick recap, what we derived last time is that we started with the equations of motion, which have like the standard equation part, first part here, which have then the external forces, the contact forces, and which have the actuations as submodules. We then did a hard contact analysis. So we said we have a constraint which says that this point here is not allowed to move, and that this constraint creates this interaction force with the environment. We derived interaction forces, and then we looked at the support consistent dynamics, which was essentially a null space projection that we do with the equation up here, which makes sure that this contact force drops out and gives us an equation which is then only depending on the two variables, on the torque and on the motion. And again, I have here q double dot while meaning u dot, but this is just like because I'm sloppy in the writing, like everybody else is writing a paper. Now I can do standard inverse dynamics with that. All I have to do is like I have to take this component here, make the pseudo inversion of that, and what I get is give me a certain motion, and I tell you what kind of joint torque you need in order to achieve this motion. And then this motion that we give as a desired motion in here, of course this motion has to satisfy the tasks we want to achieve, and it has to satisfy the constraints with the environment. Now, as we know, there is multiple solutions to these problems because we have here a pseudo inversion, which means that there is again a null space projection matrix of this NCT times ST, which results in a tau 0 that allows us to modify the desired torque without modifying the tasks that we want to achieve in motion space. So what this is in essence, this part here is the internal force directions. So I can change the force with the environment without changing the motion of the system. So this in here will have a influence on Fc while not having an influence on Q. Instead of like doing purely inverse dynamics control with this support consistent dynamic description, we can also revisit the quadratic programming solution we looked at before, but now for the full dynamics equations of motion of a floating based system. Remember what we did last time is we looked at an equation. We said mq double dot plus b plus g equals to tau, and we had a number of tasks, j times q double dot plus j dot q dot equals to a certain task space velocity, and we wrote this as an optimization problem in two parameters, namely in q double dot and in tau. Now what we have now is not only q double dot and tau, but you also have a contact force in this floating base formulation. So what we can do is we can define now a optimization variable which is composed of these two elements. So acceleration, contact forces, and torques. And anything, whether it's the dynamics equations of motion, whether it's a motion task, whether it's a force task, whether it's a torque optimization task, can be written as a linear objective in these three, or in this variable x, which is these three variables u dot, fc, and tau. And this is what we do in here. So instead of writing the dynamics equations of motion for floating based systems in contact with the environment, we can formulate this in matrix form as an A matrix and a P vector, and this is then fulfilling the equations of motion is the least square minimal solution of minimizing ax minus b. In fact, since we always have a solution, this in here we can write that ax equal to b. It's not only an optimization, it's really a constraint. Then we can do the same thing for motion tasks, whereby here we have only dependency on the acceleration, so we have only the first element in our A matrix, which is filled. Then we can also write force optimization tasks, and we can minimize, for example, joint torques. So what that means is now like very complex control problems. Like, for example, I want to move my end effector while moving the base, while ensuring a contact constraints, while minimizing the joint torque of a n-dimensional humanoid system, can be simply written as a set of quadratic program. And all we have to do is we have to convert these individual tasks into these A matrices and B vectors, and then solve for x. So figure out this x, while these individual tasks have certain priorities. Now what you see here is the most generic description of an inverse dynamics based controller for complex floating based systems like a quadrupedal system or a humanoid system, and we're gonna see in the next lecture in how we apply exactly this technology to quadrupedal robots. Thank you very much.